Today's topic, I'm going to first talk about an extension of that tandem queue called a transfer line. Basically, if you remember, we kind of took the multiple server queue and said, okay, what if there are two of them? When you go from when you leave one, you go to another. What the transfer line does is it generalizes that, says, what if we have n of these in a row? And then following that, I'm going to talk about a way of componentizing these, because what it turns out that there's a lot of value, instead of creating one event graph to do the whole simulation, to creating components, pieces of of event graphs, and then connecting them together through something called SimEventListening. And that uses the same idea of listening for events that we've encountered, we've encountered when doing graphical programming in Swing, when action events were fired by a button and that was heard by something else. So it's kind of the same, a similar kind of idea, but it applies to these event graphs, and we'll see what that's about. Okay, and then we'll apply that to, again, this multiple server queue that we've been torturing to show how to kind of componentize that. Okay, so what is the transfer line? The transfer line is a generalization of that tandem queue, and its name kind of comes from a type of manufacturing process where you have a sequence of workstations, and each workstation does one task to a job that, as it gets processed by each sequential station, eventually comes out at the other end as the completed part. So the idea is that in the tandem queue, we went to one server or one station, and then when we were finished at that first station, we went to the next station, and then we were out. So that works for two, but what about many? What if you have many of these things? And I mean, in a way, that the tandem queue, if you kind of squint your eyes a little bit, you can kind of, it's kind of analogous to an assembly line, which I'm sure you're all familiar with how that works, where you have these car parts that are basically sort of the skeleton of a car, kind of goes from one workstation to the next and gets executed. What's different is that in the assembly line, there's no queuing; it just kind of keeps going. Whereas with the transfer line, the idea is that it's structurally the same as an assembly line, in that you have a sequence of these tasks. The difference is the queuing. So at each workstation, you have a particular number, which is in principle different from at each workstation. So at the first workstation, you might have 3 machines or servers, and at the next one you might have 5, and at the next one you might have 1 or 2. So the idea here, again, each workstation is being modeled as a multiple server queue. So when you leave one station, you go and wait in line at the next station. And if you can be served immediately, then so be it. If you can't, then you wait in the next queue. So how do we turn this into an event graph model? Well, we always start with our parameters. So as always, we have arrivals from outside the system, and they always go to the first workstation. So just like with the tandem queue, nobody starts at the second workstation. Likewise here, nobody starts in the middle, everybody starts at the beginning and proceeds to the end. One parameter is going to be just the number of workstations. How many do we have? So the idea is that the idea is parameterizing a model is that instead of writing a separate model having to write a separate model for 2 and 3 and 4 and 5 stations. By making it a parameter, the same model template, if you will, can work for any number of workstations. Now, since we have n of these workstations, again, we're going to number them with this silly zero-based indexing. So because each workstation can have a different number of machines, we need to specify that basically as kind of an array. So k sub I are going to be the number of machines at workstation I. And there are going to be n of those, which are going to be indexed 0 through n minus 1, just like a Java array. Similarly, because the service time at each workstation is distinct from each other, we need to have a separate sequence of service times for each workstation. And in most of in the implementation, that's typically going to be done with an array of random variables. So just as our parameter for the number of machines would be an array of integers, the parameter for the service times would be an array of random variables. Or, again, we can, but for the purposes of an abstract event graph model, we can just simply think of it as some arbitrary sequence. Okay, state variables. Now, because a single state variable, let's say for numbering Q, that's kind of the way we've been modeling these Qs. But you see, we can't have just one variable Q to say how many are in the queue, because so let's say if there are, say, 4 in the queue and we have 3 workstations, we don't know where they are. And we need to know how many are in the queue at each workstation. And so again, the state variable in this would be an array of integers of length n. Again, index 0 through n minus 1. So the number in Q at station I, that would be Q sub I. So the Q0, Q1, Q2, et cetera, those would all be distinct state variables. Similarly, the number of available servers at each station is going to have to be an array as well, because we can't just say, well, there are 5 available servers at which workstation. You need to know that in order for the model to have any meaning. So likewise, the number of available servers would be an array of integers of length n, and its initial value, well, the initial value for the number of available servers at workstation I would be k sub I. In other words, at the ith workstation, you start off with k sub I available servers, or sometimes I'll refer to them as machines, because that's typically what you have there. Again, if you remember, one of the kind of motivating systems that we can think of is the DMV. We use that as kind of a motivation for the tandem queue, but if you have ever experienced the DMV, you'll notice, you'll probably recall that there are more than one stations you have to go to. So this transfer line would be a reasonable model, at least as a first cut at modeling a DMV, where again you come in at the beginning, you have to proceed in a specific sequence of service until you've checked all the boxes. In other words, you've received service at each one of the workstations in sequence, and then you're finished. And no doubt there are other situations that you've encountered where you have where you as the customer have experienced something like this, where you go, you wait online at the first station. When you get finished there, you go to the next one, and when you're finished there, you go to the next one. And at each station where you go, if there's a line, then you have to wait in line until it's your turn. So that's what we're modeling here. Okay, so here's the event graph. So rather than kind of going through it in piecemeal, this event graph is also in the reading. So what I'm doing is just try to break it down in terms of some of the pieces. So if you remember yesterday, we looked at this for loop idea of how to implement a for loop in the in event graphs. Now, if you're thinking about just a pure computer program, and I have an array that I need to initialize, how would I do that? Well, you would use a for loop. So you in a regular computer program, you would write it as a for loop. But here in event graphs, what do we need to do? We need to initialize every state variable. And so we can use that structure of the for loop that we talked about yesterday to initialize our state variables S and Si and Qi. And here's how that works. So again, just focusing on this initialization piece here, we see that when run occurs, for crying out loud, run will schedule init passing 0. So init 0 will occur, and when init 0 occurs, it will set S0 to equal to K0, and it will set Q0 equal to 0. Okay, so that first station has been initialized. Then, if this index, I, is less than n-1, remember n is the number of workstations, it will schedule another init passing I plus 1. And then it's done. If you remember the event list that we saw yesterday, we saw that just the init would happen one after the other. And that's important to know how the event list is processing things. So now the init, the next one would be the init init 1. So we had init 0, that's scheduled init 0 plus 1, which is 1. So let's say n is equal to 3, just for the sake. Okay, so init 0. Okay, what is the check? If n is 3, n-1 is 2, 0 is less than 2, that's true. So we schedule init 1. And then, then the init 0, the init event with the 0 parameter is done. It's out of there, it's gone forever. Then, but the event list now has init 1 on it. So init with a parameter of 1 will take S1 and set it equal to K1, and Q1 and set it equal to 0. So after that gets executed, the 0th and first elements of S and Q arrays have been initialized. Now I is 1. Again, n is 3, so 3 minus 1 is 2. Is 1 less than 2? Yes, it is. So we schedule init 2. And when that occurs, S2 is initialized to K2, and Q2 is initialized to 0. Now we look at our Boolean condition, I is 2, n-1 is 2. Is I less than 2? Is 2 less than 2? No, and so this does not occur. So at that point, we have initialized all of our state variables in the arrays, and that is that's basically what that piece is doing here. Now, simultaneously, the run event has also scheduled the first arrival, and notice that it has some delay of an inter-arrival time. So what that means, and again, this gets back to the importance of understanding how the event list works. Even though this arrival event was scheduled at the same time as the init event, and it might even be scheduled beforehand, its scheduled time of arrival is going to be sometime in the future, because the inter-arrival time is going to be positive. So this arrival event, this first arrival event, is going to be sitting on the event list while all of these init events are spinning around at time 0. Okay, so it's important to understand that. But then when the init events are all finished, then the event list looks at what's on the event, the event list looks and says, there's one arrival event on the event list. So it will move time to that first arrival. In this particular case, the arrival, we could have put the n+1 there. We didn't. Doesn't matter. The thing to notice is that here we have an event whose state transition is the identity. In other words, it doesn't actually change any value, and that's kind of by design, just to show that an event does not necessarily have to have a state transition. Usually it does, but in this case, the only purpose of arrival, this arrival event, was to schedule that arrival to the 0th station at the transfer line. Okay, so just focusing on this arrival event, what it will do is it will schedule the next arrival sometime in the future. So it does two things. Again, notice there are no conditions on either one of these edges. So it will schedule the next arrival, which will happen sometime down the line, and it will schedule with 0 delay this arrival passing the value 0. And then it's done. So after that first arrival event is executed, there is going to be an arrival event with a 0 argument and an arrival event with no arguments sometime later. So at time, at that first arrival time, this arrival event with an argument of 0 is going to be on the event list, and another arrival with no argument is going to be on the event list sometime later. Now, if you remember what method overloading was about, method overloading was the idea that you could have two methods that have the same name, but if they had different signatures, they were different methods. A same thing applies here, or a similar thing. So here we have two events called arrival. This arrival event has no arguments. This arrival event has a single argument that's an integer. And so these are two completely different events. And the event list will keep track of which is which. So what will happen after that arrival is that, and when it exits, there will be one arrival event with an argument of 0 happening at the same time, and another arrival with no argument happening sometime in the future. So what does the event list do? It processes the earliest event, and in this case, the earliest event is going to be the arrival event with a parameter of 0. Okay, so let's look at what happens there. So the arrival event with an argument of 0, it increments q sub I. That is, it increments the number in q at workstation I. That's all it does. Then what it does is, if at that first workstation, that is, if S0 is bigger than 0, then it will schedule a start service passing the value I, which in this case is 0 for that first one, to start service. And then notice that that's the only possible scheduling event, a scheduling edge for this particular arrival. So, and then it's done. Now for that very first arrival, presumably this condition will be true. That is, at the very beginning, we have an available server. So the very first time, this will be true. And so the start service event with an argument of 0 will be scheduled. And this arrival event with no argument is still on the event list, but that's going to be sometime in the future. And so when the arrival 0 event completes, it then control passes back to the event list, and the event list looks and it says, okay, I have a start service with the parameter of 0 at this time, and sometime later there's an arrival event with no argument. So what's the first one? The earliest one is the start service event, which has happened at this first arrival time. Okay, so Start service receives a 0, and notice that that argument, is what is used as the index of the state transition. So this says the number of available servers in this case, at the 0th workstation is decremented by 1, and the number in the queue at the 0th workstation is decremented by 1. Again, we're doing it for I equals 0. And then it looks to schedule. So it has one scheduling edge, and the delay is TSI. That is the service time at the ith workstation. And when it schedules the end service, it passes the value I. Now, that's important, is that whenever you're scheduling an event that has an argument, you must pass the parameter. And the parameter must be in the box that's on the scheduling edge. That's like invoking a method that has an argument. If I have a method called, let's say, do end service in this case, and it has an argument that's an int, then when I invoke it, I need to pass it that argument. Now, a scheduling edge doesn't invoke directly. It's the event list that eventually does that. But when, in this case, start service schedules that end service event at some time later and passes that argument, then when the end service event occurs, that parameter is going to be part of how the event list figures out whether or not to invoke this event. And so if this parameter is not there, then there's no match with this event, because if there's no parameter, it's looking for an end service event with no argument, and there is none. So start service passes this argument I, which it received from the arrival. And the very first arrival received it from this arrival event with no argument. Okay, so that 0 gets passed here first, and then gets passed to the start service with the 0, and then the 0 gets passed to the end service event. Okay, let's look at what happens with the end service. Now, again, we're just doing the first one. So the end service will occur with a 0 argument. We now increment our number of available servers, and we have 2 scheduling edges from end service. So the first one, or again, they're actually in no order. So one of them says, all right, if Q is bigger than 0, that is, in this case, since I is 0, it says if there's a customer in the queue when we finish service, we're going to schedule another start service, and we're going to pass it our value I, which in this case is 0. So an end service event with argument 0, when that occurs, if there's nobody in the queue at the 0th workstation, then it will schedule a start service event, passing it the parameter I, in this case 0. Okay, that's one scheduling event edge. But notice that there's another one, and this one goes all the way back to arrival, and let's see what that's about. It has the condition is all the way down here, and the condition is I is less than n minus 1. What does that mean? That means that, see, I can be any value between 0 and n minus 1. The idea here is that if we are not at the end of our line, if you're not at the end of the line, then you want to schedule an arrival to the next workstation. And here's how that works. This is kind of similar to what was going on with the init event, except, and in fact, you can sort of think of it as this giant for loop that kind of goes across several events. So if I is less than n minus 1, then we schedule an arrival, but then we pass I plus 1. So for our end service with a 0 argument, if there's a second workstation, And how can we find that? So let's continue with, if let's say n is equal to 3. So if I is 0, 0 is less than 3 minus 1. That's true. So it will pass 1 to arrival. And so now nService will schedule an arrival event with argument 1. So now at this point, there are now 3 events on the event list. We have a start service event that's happening at the same time as the end service event, and that's happening at time that has an argument of 0. We have an arrival event with an argument of 1, and then we can't forget this arrival event that's not going to be on the event list at some time. There's notice that because every arrival event schedules another arrival, then as long as the simulation is running, there's going to always be some arrival event on the event list sometime in the future, except when that arrival event actually occurs, of course. Okay, so then now which happens first? Now it turns out it doesn't really matter, because the start service with 0 is not going to impact the state variables at station 1. So start service only affects the arrays, the state variable arrays in the 0th place. This arrival event with an argument of 1 will only affect Q of 1. So the order that these events are going to be occurring in, even though they're happening kind of simultaneously, the order in this case doesn't matter. So the arrival event 1, again, the start service with 0, again, it will schedule another end service with 0 if that's the case. And if not, then it'll just kind of sit there waiting for the next arrival at station 0. In the meantime, let's look at arrival 1, just to kind of beat this poor dead horse. So arrival 1 is going to increment Q of 1. And then if there's an available server at station 1, it will schedule a start service passing the value 1, etc. Okay, so that's how this event graph is going to work. And and it's useful to kind of just look at the pieces to see three of the patterns that we've encountered. Kind of in the middle here is this arrival pattern, this arrival process pattern. At the top is this for loop pattern that we've seen, that we saw yesterday. And at the bottom is this kind of looks the way the multiple server queue looked. We had an arrival, start service, and end service. We had similar kind of state transitions. And the only differences are the fact that we have arguments on each of the events. We're passing those arguments through, and then at this end service, instead of just kind of leaving it, this end service event conditionally schedules an arrival at the very next station. So even though at first glance, this kind of looks like a lot of noise, when you look at all the pieces, you see that it's built up of pieces that we've already encountered. And in a way, that's kind of the motivation for what comes next. In other words, instead of, if we're going to if we want to build bigger models and models that are kind of more flexible, it will be very helpful to take these pieces and build up a library of these different pieces or components, if you will, and have the ability to kind of connect them together. And that's what this SimEventListener idea does. So the idea here, each of these boxes here, this is kind of a canonical representation. Each of these boxes consists of a separate event graph model. But they're kind of, you have a source and a listener. And this is roughly analogous to If you remember, the source of an action listener was a J button, and the listener was one of these action event listeners that we'd instantiated. So this is here, the source and the listener are actually both event graph components. And here's how it works. The way it works is that as the source event, the graph, is processing, it's scheduling events, and these events are occurring. And when it has an event, that is when one of its event occurs, it's processed normally. But then the source event gets heard by the listener. And if the listener has that event, then it gets processed by the listener as if the event, the listener had heard it. All right, so here's kind of a more, again, a slightly abstract example. But here the source is this little event graph here. So we have events A, B, and C. And in the listener event graph, we have events B and D and G and F. And that's just, what are those? Those are just the names that have been assigned to those events. Now, at some point, events B and C are going to be scheduled. Okay, notice that event A is actually not, in this case, how does A occur? Well, maybe it's heard from somewhere else. But event B will be heard by the listener. Event C will be heard but not responded to. And event A won't be heard because it's scheduled, because it's not scheduled by this source component. And now notice this, the connector has kind of two ways of thinking of it. One is you can think of this arrow as the way that events are being directed. So an event in the source gets transmitted to the event in the listener. Or you can think of it from the listener's perspective and think of this like a little stethoscope that the listener is kind of listening in to what's going on in the source event. So here's how that might work. So here, let's say event at some point occurs, how, by hook or by crook. And it will schedule events B and C. And at some point, event B is going to occur. And when event B occurs, the listener will hear B and schedule D. But when C occurs, and I haven't animated that, it will be heard but not responded to. But you see how this kind of works. All right, so let's apply this to our this multiple server queue that we've been torturing to death. So the idea is that instead of creating the entire model, we've noticed that this arrival process pattern of the arrival scheduling itself just appears time and time again. So let's treat that as a separate component and then have another component that's just going to be the server part of the model. So we're going to not worry about the arrival sequence. We're just going to assume that somebody else is doing that. That's the analogous to the programmer virtue of that's not my job. So it's not going to be the job of the simple server component to model the arrivals. It's just going to respond to arrivals. And so in order to work, it's going to have to listen to another component that schedules the arrival events. The arrival process is one example. But, and this is where the flexibility comes in. Any component, any event graph component that schedules arrival events can be used to drive the server component. So let's take a look at how that works here. So the simple server component is now going to have only two parameters, the service times and the number of servers. It's not going to have the inter-arrival times as our multiple server queue model did. So we leave those out. We're simplifying it. This is a smaller model. but it allows us to be a little more flexible. And our state variables are going to be kind of similar. So we'll have the number in the queue, we're going to have the number of available servers, and the number of service completions. Yeah, we're going to call that N. I think we called that L before. Don't call it late for dinner. Okay, so here's what that simple server component looks like. Now notice that it resembles the multiple server queue, but it's a lot simpler. So first of all, it has the arrival event, and that arrival event has exactly the same state transitions as we had before. It increments queue, it schedules the start service event, and all of these events act exactly the same as they did previously, with the exception that the arrival event does not schedule another arrival. The second important difference is that notice the run event, while it initializes the state variables, it does not schedule anything. And that's because the simple server component, the idea is the server is just going to sit there waiting to hear some arrival event from somebody. And when it hears that arrival event, it will carry on with its state transitions, with its scheduling, and everything proceeds from there. Until it hears an arrival event, it's going to do nothing. So the way that we put this together with the models, we take that arrival process that we've been doing for, since almost day one. So we treat that as a component, and it will produce a sequence of these arrival events, and the server will hear those arrival events. And as it hears those arrival events, it will schedule them. So actually, here's how it kind of looks in a little more detail, opening up the box. So here's our arrival process that we had before. It's just identical to what we had. And here's our server component. So the server component, again, it does what it does. So here's how this is going to work. Now, when you have this, there are actually going to be 2 run events on the event list at the very beginning. When and this is actually the next model that I'm going to have you implement in tomorrow's lab. So when this starts, there are going to be 2 run events on the event list, one for the arrival process and one for the server component. Now, which one happens first? And again, it doesn't matter. So if the server component one happens first, all that does is initialize its state variables, and that's it. It doesn't schedule anything. But then the run event in the arrival process is going to schedule its first arrival and then be done. So now the event list is going to look, it's going to say, okay, I've finished, I have no more events of run, but what's on my event list? An arrival event to occur at some time in the future. So we move time up to that arrival event, and that arrival event occurs. Now that arrival event will increment this state variable in the arrival process, schedule the next arrival, but then the server component will hear the arrival. And then when the server component hears the arrival, it says, okay, I heard an arrival. I'm going to increment queue. And then if I have an available server, I'll schedule start service and keep going like that. And in the meantime, so let's say, let's look at the very first arrival. The first arrival will schedule another arrival of the arrival process in the future. And the arrival of the server will hear it at that time. And it will schedule a start service with 0 delay, because the very first arrival will actually have an available server. So then the arrival event is finished. The event list looks and sees what it has. What does it have? It has a start service event at the current time, and it has another arrival event from the arrival process at some future time. So what comes first? Well, in this case, the start service event would come first. And so the start service event would get processed and then keep going. Now, as the simulation progresses, events from both the server component and the arrival process are being put on the event list and being processed according to exactly the same rules, whichever one comes first. The difference is that whenever an event scheduled by the arrival process occurs, it gets basically sent back to the arrival process. In other words, when the arrival event from the arrival process is processed by the event list, then this is what gets executed. And let's say when the start service event occurs, then it gets processed by the server component. So the event list basically hands the event back to the component that scheduled it and said, here, do your thing. And when you're done, I'll do my thing. The other important thing to observe is that notice, and this was kind of deliberate, notice that there's a state variable called n in the arrival process, and there's a state variable called n in the server component. Now, just because they have the same name, doesn't mean that they're the same thing. They are actually completely different state variables. So the arrival event, the arrival process event n, will simply count the arrivals as they occur. The n state variable in the server component will only count the number of customers that have been completed service. So at any point in time, the arrival process's n is going to be greater than or equal to the server component's state variable n. But in a sense, they're really completely apart one from the other. And a way to think of this is if you think of these as two distinct objects, then if I have an object that has an instance variable and another object that has an instance variable that happens to have the same name, they're completely different things, completely independent of one another. Okay, so that's that's what's going on with that.